Active electrosense is a biological sensing mechanism used by certain weakly electric fish for object detection. These fish generate a weakly electric field around themselves and sense objects based on how much they distort that field. Northwestern's NXR lab has implemented a robotic version of active electrosense, as seen in this gantry setup, and in this project we'll show how we can use electrosense to classify objects, specifically spheroids, based on their aspect ratio. Due to the time constraints and the incomplete setup of the current gantry and robot, we're actually using COMSOL to simulate the electrosense data. However, the results should be pretty much the same. So the distortion in the field is detected as a voltage profile. When the object rotates, this voltage profile will also change amplitude. So as you can see, for our training data, we have simulated 4 different spheroids of varying aspect ratios, so with AR1, AR2, AR3, and AR4, and we've obtained a voltage profile of the object for every 45 degrees of rotation.
The raw data was in the form of a 5 by 101 matrix. We added Gaussian random noise to the data with standard deviation that was 10% of the maximum voltage seen on each of these. We originally wanted to process our raw data by fitting polynomials to the voltage profiles of each of the degrees of rotation. This would reduce our features to 5 sets of polynomial coefficients. However, at higher aspect ratios, this required very high degree polynomial, which overfit the curves of the lower aspect ratio. When we then simplified more by extracting the amplitude and the width at 1 degree of rotation and found that our features really just collapsed onto this one line. So we decided to train a least squares fit using the amplitude at 0 degrees.
We used least squares regression to fit the amplitude versus the aspect ratios, as you can see that here in figure 4. Based on the training data, we suspected that the model would be linear and tried to verify this using cross-validation. We used cross-validation to select the best degree of polynomials out of degrees 1, 2, and 3. From figure 2, you can see that the first degree polynomial performed best. We also compared this to a least squares fit to the square root. From figures 5 and 6, you can see that the linear model still performed better based on total squared error. We tested this linear model generated with the data from aspect ratios 1, 2, and 3, and 4 with an unknown aspect ratio. The model predicted that the aspect ratio was 2.6, and it was in fact 2.5, so it was able to predict the aspect ratio within an accuracy of 5%. Our conclusions from this experiment is that for a given spheroid object, we can determine its aspect ratio to an error of plus or minus 5%. Thank you.